Have you ever wondered what a piping engineer really does? Or are you a project manager looking to understand their role? Did you know there's a document that should not have an as-built version? And the bund wall height and width, not determined by civil engineers. Who's responsible then? What about platforms and ladders, not designed by structural engineers? Stick around, you might be surprised. Welcome to Piping Design with Long. In this video, we'll explore a critical topic, the scope and workflow of piping design in EPC projects. Let's begin with why piping design matters. Piping design has a major impact on both the project schedule and cost. According to the book Pipe Stress Engineering by L.C. Peng and T.L. Peng, piping accounts for 25% to 35% of the material cost in a process plant, requires 30% to 40% of the erection labor, and consumes 40% to 48% of engineering man-hours. That's massive. So understanding piping design scope is not optional, it's essential. Now, what exactly does piping design scope mean? It refers to three key questions. 1. What are the piping design deliverables? In other words, what documents must the piping department produce? 2. What inputs are needed to create those documents? Do we need 100% of the inputs before we start the work? 3. What's the purpose of each document for engineering, procurement, and construction teams? We'll walk through each document with these three aspects in mind. Let's start with early-stage deliverables. There are three: plot plan, piping material specifications, piping design criteria. What is a plot plan? A plot plan is a scaled drawing that shows the layout of equipment, buildings, roads, pipe racks, and other facilities in an industrial plant. It acts as the master plan that guides placement and spacing, making sure all elements fit, function, and are constructible. What might surprise you is the significant amount of information the piping engineer is responsible for at this stage. This includes determining fire pump and tank placement, road widths and paths, boundary wall heights and widths based on fire safety codes, as well as pipe bridges and trenches. Essentially, the piping engineer plays a role similar to that of an architectural designer in the oil and gas industry, shaping the layout and infrastructure to ensure safety, functionality, and compliance. That's why a plot plan should be designed and even drafted by a senior piping engineer with at least 10 years of experience. You might ask, why does a senior engineer need to draft it? It looks simply just lines, circles, and rectangles. But its impact on safety, constructability, and cost is enormous. In fact, if you had to name the two most important documents in an EPC project, the first is the PFD, and the second is the plot plan. What are the design inputs required for a plot plan? 1. Civil survey and site layout, topography, elevation, access roads. 2. Process flow diagrams, major equipment and connectivity. 3. Process engineering data, flow rates, pressures, utility needs. 4. Client specifications, spacing, safety zones. 5. Local codes and standards. 6. Project plot allocation, zones for utility, admin, future expansion. 7. Environmental and utility inputs, wind direction, water, power sources. Once the plot plan is approved, it becomes the foundation for downstream work. For example, the civil team can start piling based on the equipment coordinates provided. Now, let's look at piping material specifications, commonly referred to as PMS. PMS is a technical document that defines materials, components, codes, and fabrication standards for piping systems. It's based on service conditions like pressure, temperature, and fluid type. This includes things like pipe, fittings, flanges, valves, relevant codes like ASME B31.3, ASTM, API, pressure and temperature ratings, welding requirements, corrosion allowance, inspection and testing methods. We'll go into all of this in detail in the dedicated piping materials video. The purpose of PMS is simple but critical: standardization, safety, compatibility, procurement efficiency. Piping design criteria. The piping design criteria is a key document that outlines the fundamental rules and design assumptions used for piping layout and stress analysis. It typically includes parameters such as design temperature, pressure classes, insulation requirements, pipe spacing philosophy, flexibility and support strategy, and any special project constraints. This document serves as a reference baseline for all piping deliverables, ensuring consistency and alignment throughout the design process. In many projects, the client provides the design criteria for the contractor to follow. If not, it becomes the contractor's responsibility to prepare and issue the document for internal use and client approval. Mid-stage design, the role of 3D modeling. In the mid-stage of design, the 3D model becomes the central activity and coordination tool throughout the project lifecycle. Based on the P&IDs, the piping engineer is responsible for modeling all key plant elements, including equipment, buildings, structures, foundations, cable trays, pipe racks, and of course, the piping systems themselves. Once the piping model is developed, it serves as the primary reference for structural engineers, who then perform structural stress analysis. Based on the piping loads and layout, they determine the member sizes, connection details, and bracing configurations. After the structural model is finalized, the piping team will either update the 3D model accordingly or directly import the structural model provided by the civil structural team. 3D model reviews are typically held at 30%, 60%, and 90% design stages. The focus is on checking clashes, accessibility, routing, and constructability. Common tools used include SPR, Navisworks, and Aviva E3D. It's a key milestone to align all disciplines and catch issues early before construction begins. A critical point often overlooked: piping engineers define nozzle orientations, platform levels, how many legs and orientations, and clearances based on layout philosophy and maintainability, not based on vendor-dictated coordinates. Next, we will talk about another most important deliverable, the piping layout, also known as GA drawings. These are plan and elevation views showing routing, tie-ins, and key elevations. Almost all other disciplines rely on piping layout to begin their work. Why? Because it contains 1. Nozzle orientation info for tanks and packages. 2. Pipe support types and positions. 3. Orientation for platforms, ladders, and towers. 4. Instrument location for gauges, flow meters, etc. 5. Cable tray routing info for E&I engineers. 6. Maintenance access, lifting space, and walkways. 7. Equipment foundation orientation and elevation. Important field tip: never construct pipe support foundations before the piping and equipment are physically installed. Instead, civil engineers should design and build a simple flat concrete slab in the beginning. Once piping is in place, support foundations can be cored through and installed accurately based on the actual pipe routing. This approach avoids unnecessary assumptions and rework. In my experience, when support pedestals are pre-built based on early layouts, up to 80% end up being cut, modified, or completely demolished. That's wasted engineering effort, wasted material, and wasted labor. By delaying pedestal construction and starting with a flat slab, you save significant engineering man-hours and construction resources, while ensuring much better alignment and accuracy. What are the design inputs required for piping layout drawings? 1. P&IDs, pipe and instrumentation diagrams, process connections, instrument locations, and valve types. 2nd, plot plan, equipment locations, and overall plant arrangement. Piping material specifications for identifying piping classes and material compatibility. 4th, line list, line numbers, sizes, specs, and insulation requirements. 5. Equipment, general arrangement drawings, orientation and nozzle coordinates of tanks, pumps, vessels, packages. 6. Instruments. 7. Electrical and instrumentation requirements, cable trays, junction boxes, instrument takeoff points, and minimum separation distances. 8. Client specifications and design philosophy, minimum clearances, maintenance space, accessibility, fire zones, and safety codes. 9. Project 3D model coordination, if available, for clash checking and visual planning. Important note for piping designers: you do not need 100% of the design input to begin your piping layout. In real projects, some vendor data like pumps, skids, and instrumentation may not be available in the early stages. To proceed, use typical dimensions or library models based on experience. Clearly cloud the area and mark as on hold in the drawing. Issue the layout as issued for approval while waiting for final vendor info. Once data and reviewed comments is available, update to issued for construction. Next, let's talk about pipe support standard drawings. These are technical documents with pre-designed support types: shoes, anchors, spring hangers, etc. They include dimensions, pipe size, applicability, welding and fabrication details, material specs, reference codes used in isometrics. These standard drawings speed up the design and avoid repetitive calculations. Companies like Shell, Worley, and Modec all have their own support standards. If your client doesn't have one, clarify early. Ideally in the tender phase, you may propose using Shell DEP or another standard. Otherwise, you risk getting stuck calculating support strength for every single pipe. I've seen it happen. It's a nightmare. Other mid-stage deliverables include preliminary MTO, material takeoff, a preliminary estimate of material quantities used to support early procurement planning. Based on this MTO, the procurement team can issue requests for quotation, RFQs, to vendors and may proceed to purchase up to 50% of the required materials for early construction activities, such as underground piping, long lead items, and bulk materials. Stress analysis reports required for critical lines with thermal movement or vibration. What are the design inputs for pipe stress analysis? 1. A client's pipe stress analysis specification. It outlines the criteria to determine which lines require evaluation, load cases, allowable displacements. It defines support philosophy, special cases like GRE or buried piping, and documentation requirements such as stress reports and software to be used, etc. 2. Piping isometric drawings or 3D model PCF file, which can be directly imported to Caesar. 3. The following details are required: line routing, lengths, bends, branches, elevations, support locations and types, anchors, guides, etc. 4th, line list, line numbers, sizes, design and operating pressures and temperatures, insulation, fluid type and phase, liquid, gas, or two-phase flow. 5. Piping material specifications, material grades, allowable stresses, corrosion allowance. 6th, P&IDs, confirm process conditions to highlight the analyzed pipeline and attached in the stress report. 7. Design codes and standards, typically SME B 31.3 for process piping, B 31.1 power piping, etc. 8. Equipment nozzle, allowable loads, vendor data sheets for pumps, compressors, exchangers, tanks, etc. 9. Support and restraint philosophy guide, limit stops, anchors, spring hangers, constant supports, structural constraints or platform integration. 10. Thermal expansion, data temperature changes, minimum and maximum design temperature, operating and ambient. 11th, sustained and occasional loads, pressure, weight, pipe plus fluid plus insulation, wind, seismic, and occasional loads, snow or blast loads if applicable. 12th, equipment movement, structural movement, or displacement. For pipes connected to tanks or vessels that may expand, settle, or shift. 13. Slug flow or two-phase flow, dynamic loading for certain services, flare lines, condensate return. Design tips. If no allowable load data is available at a tie-in point, treat it as a pressure vessel nozzle and evaluate against ASME Section 8, Division 1. This approach provides a conservative and code-compliant basis for stress analysis in the absence of vendor data. We'll dive deeper into stress analysis, including load cases, nozzle loads, and special situations in the upcoming chapters dedicated to pipe stress analysis. You don't need 100% of this data to start your stress model. Here's what you can do. Start modeling based on the isometric layout and known conditions. Assume vendor nozzle loads using typical values, API 610 guidelines for pumps. Make an assumption list in the report for any unknown parameters issued for approval, and finalize it once actual vendor data is received. Tip: clarify in the tender stage which lines need stress analysis. Many client specs are overspecified. Pipe stress is about expansion and contraction, not size. A 2-inch hot line may need it more than a 24-inch ambient one. Offshore piping stress is also far more complex than onshore. Trust me on that. In the later stage of design, you'll finalize isometric drawings with dimensions, welds, and support details. Important: clarify isometric drawing format in the tender. I've seen requirements like show gasket thickness as 3 millimeters and dimension it. That's an extra hour of work per drawing. Multiply by 10,000 ISOs and you've just blown your schedule. Construction culture has changed a lot over the years. Back in the 1990s and early 2000s, piping layout drawings were enough for the construction team to complete the piping work. They would even refer to the P&ID for better understanding. But by 2017, I saw that construction teams were relying solely on isometric drawings. One site supervisor didn't even carry any drawings. He asked me directly how to install a flexible hose. Times have changed. Final MTO used to verify procurement and buy remaining materials, insulation and painting specs, often already provided in project specs, tie-in list for interface with existing facilities, design changes and TQ process. During design or construction, issues and deviations may arise that require clarification or modification. These are formally addressed through a technical query, TQ, or design change notice, DCN. The piping team evaluates the query, provides an engineering response, and updates the relevant documents if needed. This ensures traceability, alignment across disciplines, and smooth implementation in the field. Finally, we reach the completion stage, as built. The construction team provides red-marked drawings, and the design team updates the 3D model, piping layout, isometrics, and other documents. One warning: never request as built for pipe stress analysis. Why? Because if the constructed pipe deviates from the stress design, there's a 90% chance it will fail the stress check. That means redesign, reanalysis, and rework. The pipe stress report is final when it's marked approved for construction. After that, any change must be reanalyzed before construction, not after. The golden rule is construction must follow the stress isometric exactly. In summary, piping design is a high-impact, high-stakes discipline. Understanding its scope, deliverables, and workflow is essential for every piping engineer. Thank you for watching. If you found this useful, please like, subscribe, and stay tuned for more videos in the Piping Design with Long series. See you in the next one.